Deep Vision, Exploring Convolutional Neural Networks. Introduction to Deep Learning and Neural Networks. The journey of convolutional neural networks began in the 1980s with the work of Yann LeCun and his team. They developed the first CNN, LeNet, designed for handwritten digit recognition. Despite limited computational power at the time, LeNet laid the foundation for modern deep learning. The 2010s saw a revolution with the advent of GPUs and large datasets like ImageNet. Groundbreaking architectures like AlexNet, introduced in 2012, demonstrated CNN's potential by achieving record-breaking accuracy in image recognition. Today, CNNs are indispensable in fields ranging from healthcare to autonomous driving, proving their significance in advancing artificial intelligence. Foundations of CNNs. Convolutional neural networks are a class of deep learning models specifically designed to process data with grid-like topology, such as images. CNNs are widely used for tasks like image classification, object detection, and segmentation due to their ability to automatically and adaptively learn spatial hierarchies of features. Key components of CNNs. Convolutional layer extracts features from the input data using a set of filters, kernels. Mechanism. Each filter slides, or convolves, over the input data to produce feature maps. Filters capture local patterns such as edges, textures, and more complex structures in deeper layers. Output. Feature map. ReLU. Rectified linear unit. Activation. Introduces nonlinearity to the model, allowing it to learn complex patterns. Pooling layer. Reduces the spatial dimensions of the feature maps, decreasing the computational load and improving the model's robustness to spatial variations. Types. Max pooling. Takes the maximum value in a local region. Average pooling. Takes the average value in a local region. Output. Downsampled feature map. Fully connected layer, dense layer. Combines the extracted features to make predictions. Mechanism. Flattens the feature maps into a 1D vector and applies traditional dense connections. Softmax or sigmoid output layer. It produces probabilities for classification tasks. Softmax, used for multi-class classification. Sigmoid, used for binary classification. Core concepts in CNNs. Convolution operation. The core operation where a kernel, small matrix, slides over the input to compute a dot product with the input's local region. Padding. Purpose. Maintains the spatial dimensions of the input after convolution. Types. Valid padding, no padding. Results in smaller feature maps. Same padding. Adds padding so the output dimensions match the input stride. The step size of the kernel as it moves across the input. Larger strides result in smaller feature maps. Receptive field. The area of the input that influences a particular feature in the output increases with more layers. Advantages of CNNs. Parameter sharing. Reduces the number of parameters, making training more efficient. Local connectivity. Focuses on spatially local patterns, leading to better feature extraction. Hierarchical feature learning. Builds complex features layer by layer, starting from simple edges. Typical CNN architectures. LeNet 5. One of the earliest CNNs designed for digit recognition. AlexNet. Popularized deep CNNs by winning the ImageNet competition in 2012. AgNIA. Demonstrated the benefits of using deep networks with small filters. ResNet. Introduced skip connections to address the vanishing gradient problem in very deep networks. Inception. Used multiple filter sizes at each layer to capture various features simultaneously. How CNNs process images. CNNs leverage two key principles, local connectivity and translational invariance, to efficiently process images and extract meaningful features. Local connectivity. Concept. CNNs focus on small regions of the image at a time, known as the receptive field. Each neuron in a convolutional layer is connected only to a local region of the input, not the entire input. Rationale. Images have local patterns, such as edges or textures, that are spatially localized. This approach reduces the number of parameters compared to fully connected networks, improving efficiency and generalization. Example, a 3x3 kernel slides across an image, capturing the features of its local 3x3 regions. Translational invariance. Concept. CNNs are designed to recognize patterns regardless of their position in the image. Achieved through shared weights. The same filter or kernel is applied across all regions of the image, allowing the network to detect the same feature anywhere in the input. Pooling. Downsampling layers, for example, max pooling, summarize features in a region, reducing sensitivity to small shifts or distortions in the image. Result. If an object moves slightly within an image, the CNN can still detect it effectively. Feature extraction in CNNs. Feature extraction is the process of identifying meaningful characteristics from the raw input data, enabling the model to differentiate between classes or objects. Layers of feature extraction. Early layers, shallow features. Detect simple patterns like edges, corners, and textures. Filters capture low-level features that are general to most images. Example, detecting horizontal or vertical lines. Intermediate layers. Combine low-level features to detect shapes, contours, or parts of objects. Example, detecting circles, rectangles, or more complex patterns. Deeper layers, high-level features. Learn more abstract representations, such as specific object parts or entire objects. Example, detecting a dog's face, wheels of a car, or even distinguishing between breeds of dogs. Examples of feature detection are edges, shapes, textures, and complex features. Edges. Filters. Edge detection filters like Sobel or Pruitt operators detect abrupt changes in pixel intensities. Role. Identifying boundaries of objects, shapes. Filters. Build on detected edges to identify shapes such as circles, triangles, or rectangles. Role. Recognizing the geometric structure of objects' textures. Filters. Capture repetitive patterns such as stripes, dots, or granular structures. Role. Differentiating between surfaces like wood, fabric, or metal. Complex features, examples. Faces. High-level features like eyes, noses, or mouths. Objects. Specific patterns of features that correspond to cars, animals, or furniture. Summary of the process. Convolutional layers. Extract features using filters applied across the image. Activation function, ReLU. Introduces nonlinearity, allowing the model to learn complex mappings. Pooling layers. Downsample feature maps for robustness and computational efficiency. Fully connected layers. Combine features to classify the input or predict outputs. Practical visualization. When you visualize CNN filters at various layers. Early layers might show filters that resemble edge detectors. Middle layers reveal filters sensitive to specific shapes. Final layers highlight features unique to the classes of interest.